Let's move on to the first lecture, that is lecture number 7 for today. Functional properties of proteins, solubility, water binding capacity, emulsification and foaming. And I hope I'll complete it in 1 hour, but it's not always the case. And I'll try to teach you as slowly as possible so you understand the basic concepts of these aspects, functionality and so on. That is the most important thing for me. And before going to functionality, I would like to show you what we have been studying so far. So we started on day 1, right? This is day 1. And we started about greenhouse gas emission, right? Right? We started with the cow. Remember my first slide? And then we thought, okay, because of this greenhouse gas emission, etc., sustainability and so on, we need to have a transition from animal-based to plant-based, right? Then on the second day, we talked about a lot about, okay, how do we get proteins out, right? Different extraction technology we got, right? What is the product of this one? The protein powder, right? Then we talked about, okay, we have a lot of proteins and how do we analyze, right? Analytical technique. What are the different techniques we have, right? Now we are getting a comprehensive understanding of the plant proteins or alternative proteins, right? We understood why we need to do this one and how we are going to do this one, and then what has to be done to better understand the structure, right? Yesterday we talked more about structure and functionality. Structure and composition yesterday. And once you know the structure and composition, I've been telling structure is a very important thing. Structure is very important thing because that determines the day 4 what we have been studying today, the functionality, right? They're all interlinked, right? Please note that food is a very complex system. At the end of the day, we need functionality, right? Somebody has to eat it, right? And eating is a complex phenomenon. Everybody is unique. Everybody has a different tongue, right? And that makes that we need to create different varieties of food. As I said, imagine dal and rice is very sustainable, imagine, but you can't serve dal and rice to the entire population. Just to give an example, we want yogurt, we want meat, we want many things. When you need this many things, we need to create new proteins with new functionalities or a better functionality or something, the functionality that's equivalent to what we have today. For example, one of the best functional food, let's say milk, right? It's a colloidal solution, right? The beauty of milk, you see that it's very stable solution. Do you agree? You go to supermarket and take the milk can and see it. It never sediments unless milk is spoiled. Unless you store it for like several months after a UHT treatment, it doesn't sediment. It's still a very stable suspension. Do you agree? It's very stable. Now, if you take meat as an example, it still have a particular texture, right? You take a yogurt as an example, it has that creaminess, right? You take a cappuccino, the coffee that you buy, the fancy one, right? It has like nice foam on the top. So we need all these different things in food so that we can satisfy human beings, so that consumers can buy them, so that we can have a business. When consumers buy, then there is a transition from animals to plants. So what I want to say here is that it's important to create different functionality to satisfy the consumers to have a transition from more animal-based to plant-based or alternative. Does that make sense? Why we need to do get the functionality? All right. So now I can ask you a question. What do you mean by a functionality as a scientist, as a food scientist?
Water holding capacity, oil holding capacity, foaming capacity, and all that it gives the texture to the protein.
So she's telling that the different properties and all thus the giving the different texture to the protein or food in general, because food contains protein, right? Texture. She's telling about functionality, something about texture. Is there anything you can add?
Characteristics of proteins that are desirable to make any desired product for the customer.
So he's thinking about it something kind of again properties, but this is not a normal property, it's a desirable properties, right? An important property that is important so that we can produce food products that consumers can buy or we can eat. It's basically creating a building blocks in my world, right? At the end of the day, texture is one of the properties, right? In addition to texture, we need juiciness, right? In addition to juiciness, sometimes we also need some sort of flavors, right? In addition to this one, we also perhaps need other properties. What would we call water binding properties, synergies, and so many other things. So all of them at the end of the day create a building block for food matrix, and that can comprehensively termed as techno-functional properties. Okay, and there's a hell lot of technological functional properties have been studied, and if you just browse in the internet functional properties of plant proteins, you get tons of them. And whenever a person isolates or extracts a plant protein for any other proteins, he or she will start analyzing as many as functional properties as possible, right? With the idea that, okay, if to find out my protein, what it has in terms of creating new building block for the proteins, for the food. Make sense? So it's very complex. There are a lot of different functional properties. The end goal is to create building block for the food. That again, as he mentions, for the consumers. I'm keep telling that functional properties related to the structure of proteins, right? It's not only the structure, but people also talk about other things also nowadays, but mainly the structure determines the functionality. And because the structure is responsible for the behavior of protein in solution and in solid state or in semi-solid state, right? Some foods are solid, some foods are semi-solid, some foods are liquids, right? So the structure of the protein that determines their behavior in different phases, right? Because the structure is nothing but different amino acid composition. We have a primary structure, we have a secondary structure, we have a tertiary structure, we have a quaternary structure, and many of these levels of protein structure determines the functionality, right? So that keep in mind. And the structure is also responsible for interaction of protein with other molecules present in food system. Yesterday I told you, protein is never alone in a food system, and nobody gonna use or can use ultra pure single plant protein in a food product. It's very difficult. I don't say can't use it. It's very difficult to get a single ultra pure plant proteins. Not possible at the moment, because that requires hell lot of processing, a lot of purification. As I mentioned yesterday, if you increase the purification, you get the low and low yield. So you can't supply the demand. So that's the problem. So remember that the alternative protein worlds today is a complex mixture of different proteins, and different proteins are associated with different components. For example, they add binding agent, they add other emulsifier, they add antioxidants, they add carbohydrates, they add fat, they add water, and then everything is mixed, everything is processed. So too many things are happening in the system. So remember one thing in your mind now when I start functionality, alternative protein is not a single protein, it's a mixture of too many proteins. Okay, whenever we say functionality in plant world or alternative protein world, it's not associated with single protein. Often it is associated with multiple proteins. For example, you are determining the pi of your p protein isolate, right? You get a pi diagram like this, right? It's pH, and this is solubility, and you say that, okay, pi of p protein is, let's say, 5.0, just to give an example. But when I say pi 5.0, it's not the pi of one particular protein in P, protein isolate. It's a generic pi of all the proteins that is present in that particular solution that gives the lowest solubility. Does that make sense? The story is different for the milk proteins, because it's very possible to isolate individual milk proteins, let's say alpha lactalbumin, beta lactoglobulin, and bovine serum albumin, alpha casein, beta casein, kappa casein, whatever. We can get it as pure as possible in an individual form, but that is not the case for plant-based proteins. So whenever you read about functionality, keep in mind that it's never an individual protein. It's a mixture. Am I clear? So whenever I talk in the next couple of slides now, don't attribute the functionality to the one protein. Think about it as a complex mixture. Okay. Now, the protein, as I said, it is never stays in alone in the solution, and the functionality is because of structure. I'm just repeating what I have taught to you last 3 days. The protein is made up of, again, amino acids, and each amino acid has its own properties, right? Some are polar, some are non-polar, some are having a charge, some are having negative charge, right? Some are having the benzene ring. Okay, some are having the benzene ring with hydroxyl group, some are having the indole ring, and these molecules are very diverse. Amino acids are very diverse. That means there is a different reaction sites on the protein. Can you see? Different interaction site or the different reaction sites on the protein, and thus they can interact differently with other proteins. When I say protein interaction, it's not only protein interaction with, let's say, carbohydrate. No, protein can interact with other proteins. Protein can interact with polyphenols, right? Everything is attributed to the structure of proteins, individual amino acids. In addition to that, the proteins are folded, three-dimensional structure, tertiary structure, and that is maybe responsible by hydrophobic interaction, hydrogen bonding, and disulfide bonds. Can you see? Now, when you start processing the food, you start changing the structure of food, right? Proteins can be folded, proteins can be unfolded, right? When they fold and then they unfold, the availability of the sites for the interaction or the reaction will change, right? In this site, for example, tryptophan is buried, it cannot interact. When you heat, maybe it denatures. Now more protein amino acids are available, maybe it is interacting differently, right? And that's also meaning that it interacts with different components with different ways depending on the three-dimensional structure of the protein. Then the functional properties can also vary. What I want to say here is when functionality is because of structure, when the structure changes even to a minor level, functionality can be changed. And that's what we do in food processing. Do you agree? We want to change the structure of processing, the structure of proteins. We do ultrasound treatment sometime, we do cooking sometime, we do boiling sometime, we do pasteurization sometime, just to change the protein structure, and that can give you different functionality by interacting with different components in that complex system. When you create a pea protein isolate or soy protein isolate or even milk protein isolate, whatever the proteins, right? It's very common that you would like to check how it behaves in water. Do you agree? It's a very fundamental thing we do in food science because almost every food contains water to a lesser or greater extent. Do you agree? Food proteins always come in contact with water. If not in the food, it will be in your mouth. So, the protein water interaction is an extremely important phenomenon we need to understand the protein functional properties, because it's the most common interaction that happens in food system, protein water interaction. Now let's little bit dig into what do you mean by protein water interaction. I know you already know all these things, but I'll try to cover some fundamentals only just to give you a better idea. Is it okay? Now I have a glass of water. I take a pea protein isolate and I put it on this one. I did not shake it. I have a glass of water. I took a scoop of pea protein isolate and put it over the glass. It might look something like that. Can you see? It's a picture from the internet. Does it dissolve quickly? No, right? What do you see actually often? You see turbidity after some time, if you shake it, right? But often what happens with plant proteins? They precipitate only after some time. If you shake it and then they precipitate. But immediately what you see? It just intermediate position, just stays on the top flowing, right? Have you seen that one? It's very normal. You take any, but it's not the case with sodium chloride, right? You take sugar or salt, you put it into water, it doesn't stay on the top, does it? It just goes down and then immediately start dissolving. Even if you don't shake it, it's trying to dissolve somehow because of change in the entropy of the system, right? But proteins are not like that. Maybe because they are big in size, right? Maybe because their particle size are so big compared to the particle size of other things. Maybe because they are not interacting with water as much as compared to sodium chloride or sugar, right? What I want to clearly say here is that proteins are different. They don't like water as such compared to other molecules, right? You need to do something. So as soon as you add protein on a water, the first thing happens is what we call wettability. That means you have a water and air interface, right? The top layer is water, then you have an air, right? Now the protein stays in that particular interface and try to wet itself. wettability. It's an important property. That's the first stage of interaction between protein and water molecule, right? And then you will slowly swirl it. Imagine, not like this one. You slowly swirl it. What happens? You start dispersing, not dissolving necessarily, right? It starts slowly going to different part of the solution and start moving inside the solution, right? So that's what we call dispersion. Basically, what happens during dispersion is you have a larger particles of proteins, right? And now it is coming in contact with water molecules slowly, and the particle size is reducing, right? That's what's happening during the dispersion. And then if you're still continuously shaking, what would happen? Dissolution. Now that is what we call solubility, right? It's a three-step. It's a lot of different steps. So the first step, you had a water molecule. The protein was staying on the top, wettability. And the second step, it start coming inside, but it's not soluble yet. Dispersed on the solution. Particle size are reducing. And in the third step, you will see dissolution. That means now water molecules will start interacting with proteins more rapidly, right? Solubility, the protein will be solubilized, right? Now, if there is a more protein than the water can dissolve, what happens? Precipitates. That's the end stage, right? Sedimentation. So these are the four basic things happens when you take a scoop of alternative proteins and put it onto water. It's rare, in the rarest case you will get a completely soluble clear solution. Do you agree with me? Of course, if you use extremely low concentration, it might get a very clear solution. I don't say no, but I'm talking about the scoop of plant proteins in a glass of water. You will always see this phenomenon. Am I clear? Wettability, dispersibility, solubility, and precipitation. These are the four generic protein water interaction we can see as soon as you put pea protein isolate, whatever isolate on water molecule into a glass of water. Now I'll ask you a question that why this is important in alternative proteins world. Can you think about why do we need all this solubility information? Why do we need all this protein water interaction? Yeah.
Because solubility is required for all other functional property. It is prerequisite for other, suppose foaming, emulsification, whatever the application is.
Yeah.
So solubility is required for.
So what he is telling that the solubility or protein water interaction is the fundamental thing that determines the other functional properties of protein, right? It has to interact with water molecule, and then perhaps it will change the emulsification property and maybe gelation properties, maybe whatever properties you are saying. It's something related to solubility. If the protein is completely insoluble, dead zero solubility, then probably that is not a good protein to be used in food system. You can use it to make a cardboard or something. I don't say there is no application. You can make it for the packaging material, for example. Protein is not only for food, it can be used for some other purposes. So you can find other application. For food purposes, you need to find to a certain degree of solubility. I don't say it has to be 100% soluble. If it's 100% soluble, probably it's very good to use it in sports beverages, for example, infant formula, for example, where it's very important to have kind of a solubility. Okay? Any other reason? Juiciness, right? If you go to KFC, we eat chicken there, and one of the things we like that crispiness. In addition to that, we also like the juiciness, right? It's a fine balance, right? And if chicken is very rubbery and dry, we don't like it. I often buy biryani somewhere in the hotels, right, in the restaurants. And if the biryani, I get this so-called breast piece and what we call, it's so hard sometimes because of it has lost all its moisture. I really don't like it to eat because I don't see that juiciness, right? Sorry, I'm talking about plant-based now. I'm talking about chicken biryani. Don't mind. In the future, chicken will be replaced by plant-based chicken. Don't worry about that. So, but we still want to get that juiciness, right? And that juiciness is something related to protein water interaction. Let's take this two examples here. It's also important to create plant-based milk, right? Milk should be milky. If milk is like a yogurt, do you buy it? Right? If milk is a hard solid, will you buy it? It's a different food. So we need different properties. So yogurt has to be soft, chicken has to be juicy, milk has to be milky. All these properties coming from protein-water interaction. Thus, of course, there are other interaction, but one of the important one is protein-water interaction. As I just mentioned, the solubility, this is again a high school thing or a primary school thing. We all studied this equation, right? Solute plus solvent is equal to solution, right? This is something I always by hearted when I was maybe in primary school. Solute plus solvent is equal to solution, because that's a common 1 marks question, right? So solute is nothing but the analyte, in this case protein. Solvent could be water, and solution is nothing but is a homogeneous mixture. It's a homogeneous. When you say a solution, we have a homogeneous solution and heterogeneous solution and so on. In case of protein, the solubility is dependent on the concentration at which homogeneous solution is formed. Okay, homogeneous solution, you know, right? Everything is in one single phase. It's called homogeneous solution, and that is called solubility. If you have a precipitate, that is not solubility. If you have a dispersion, this is not solubility. If you have a colloid, that is not necessarily a solubility. The solubility is nothing but you have a clear solution, in other words, right? And the solubility takes place in a different phenomenon. Let's try to explain that one. Now I have a beaker of water, right? I have a beaker of water, and this is me. Now I have a protein powder in my hand, all right? And then I'll add protein powder to this one, okay? I had a very small quantity initially, very small quantity, okay? And the solution is continuously under stirring, okay? We're stirring it continuously. Imagine the protein I'm adding ultra pure and having a very high solubility. I'm adding only small amount and it is vigorously being stirred. What would happen? It will completely dissolve. So we are in this particular phase at particular time, right? We have completely soluble. Please note that solubility is again dependent on temperature, pH and other things, right? And also pressure. So atmospheric pressure, temperature, pH. These are the two governing factors that determines the solubility. Keep that in mind. I'll get more details into that later. Now, I did not stop here. I add one more scoop. What would happen? It might take time, but if a solvent can dissolve that solute, that's protein here, it can still solubilize. Do you agree? Now I'll add another big scoop, little bit bigger scoop. What would happen? We are reaching the so-called saturation point. Out of that big scoop, maybe half of them soluble. The remaining half is don't want to solubilize because solute is not interacting completely with the solvent molecule. Now we are reaching the so-called saturation point, a metastable state, right? And what that time we come somewhere in this region where we are dissolving the proteins to a certain extent, and the remaining proteins will start precipitating. It's not the direct precipitation, it's what we call the first step of that precipitation is something called formation of protein crystals or amorphous particles, basically. What exactly happened here is that there is a situation where you completely solubilized proteins, and then you're adding more and more proteins now, right? And that protein would really wanted to solubilize, but it cannot, right? Then it stays in the solution as a small particle. If you add more and more particle, that will increase in its size, right? It's the nucleus will increase the size. So it's getting a bigger and bigger particle. Sometimes we call it as aggregates, right? The proteins will stay in the increasing in size. And if you still add more and more and more protein, if you increase the concentration further, what happens? Then you see complete precipitation of the protein, right? Do you agree? Supersaturation. You will get the complete precipitation of the protein. That is a system where we have two things: protein in precipitate and protein in solution. So that's where we are here. And this is how the protein solubility changes depending on the parameters. Parameters is also important. Okay? By changing the parameters, you can change this diagram. Do you agree? By changing the parameters, you can change in the paragraph. For example, some proteins need very alkaline condition to completely dissolve. right? Some protein might need mild heating. Some protein might need a little bit higher heating to completely solubilize. So by changing the parameters, we can change the solubility behavior and get the more and more protein into solution. But no matter what, at some point, you cannot solubilize, things will precipitate. Okay, and that depends upon the concentration of the protein you're adding and the temperature, pH, and other parameters. All right, so coming back to your first question, how are we measuring solubility today in the alternatives world, right? We're measuring it by three different methods. The first one is relative solubility, the second one is maximum solubility, third one is predictive solubility. The first one is the question you asked, okay? The last one is the question you asked, right? We will try to cover some of these things, okay? These are the three things we are using at the moment to determine the extent of protein solubility. Let's begin with the relative solubility. This is something most commonly you find it in the alternative research paper. What do you mean by alternative research paper? Research paper focused on alternative proteins, okay? Not alternative. This is a wrong statement, okay? You'll see that solubility analysis, they are always 90% people use this method, relative solubility measurement. It's nothing but it's not finding out the absolute maximum solubility of the given protein, just to find out the solubility of the protein you have extracted or you have purchased to in a particular condition. Am I clear? What is the solubility of a protein in a particular condition? That is relative solubility. We don't care about how much it will dissolve, how much more it will dissolve, how much less is dissolved. We don't care about it. Okay? At a given condition, what will be the solubility? That is relative solubility. So the relative protein measurement is nothing but measuring the protein under a different and a given conditions. I'm just trying to show it in an illustrative way. We take the protein, we may set the conditions, we centrifuge it, we measure the protein content, and the relative solubility is nothing but the ratio of the soluble fraction to the non-centrifuged whole fraction. That is the relative solubility. Okay, advantage is easy to do, maybe comparable with other people, but it's also a big problem. I've been reading papers on relative solubility. You can correct me if I'm wrong. It's not that everybody follow the same condition. You said 9,000, I find 20,000 G here. I also found somebody centrifuging at 6,000 because their centrifugation machine does not go to 20,000 G. Then what they will do? They'll stop doing research? No, they will increase the time. So this is a game, right? And okay, some people wants to adjust the pH, right? Every protein has a different buffering capacity, you know, right? What do you mean buffering capacity? You take a 1 scoop of pea protein isolate and shake it and measure the pH of the solution. It says 7. You take rapeseed protein and measure the pH of solution. It says 8. Soy protein may be saying some other pH. So every protein has create different pH in the solution. Then to adjust it to 7, what you will add? You add HCl, you add NaOH. Again, you're adding more and more salt, right? You know the salting in, salting out, and blah blah effect. Last time I taught you. Again, that will change. So it's not universal. Things will change depending on what you're doing. So it's not also readily comparable. And please note this point, and this is one of the challenges in comparing different research articles, comparing the properties of different plant protein isolates today. Nobody is using a homogeneous method. It's not readily comparable from paper to paper, and that's one of the challenges for food industries also. They go to great crazy. They have to do their own methods now. Make sense? So we need to find a uniform method that everybody follows to get the to do the comparison throughout the world based on if you want to compare different but it's not an easy task, just to let you know. We also covered disadvantages, and the first thing I already mentioned that it is based on specific conditions. Conditions vary. It's also depending on initial concentration. I forgot to mention that. What she mentioned that she used 10 milligram per ml. The question is that why are you using 10 milligram per ml? That's a very important point. Why? Because if I use a protein solution, it's 10 milligram per ml. Let's say it is 1% solution, right? I say my protein is 100% soluble. Do you agree? Imagine 1% is 100% soluble. If I use 1% solution, I say it's 100% soluble. Now, my PhD student will come and he thinks, no, I don't want to do 1%. I will take 10% solution, right? Then what will be the percentage solubility? Is 10%. So suddenly we change the solubility for the paper, right? Now which one will I believe? She is selling the paper saying that my protein is 100% soluble. Oh, it's super good. What is the concentration did you use? 1%. But the same your own PhD student, and he did another experiment, but instead of taking 1%, that person took 10%. Now the data will show it's only 10% soluble. So we are biased again. Am I clear? So the initial concentration also plays a role here. And now the hydration time, that's the experiment you mentioned here, is that you are stirring it continuously for 2 hours. Coming back to your own question, sometimes you do freeze drying, sometimes you do spray drying, and they have a very different properties and solubility. They need hydration time 2 days, 3 days, even sometimes 1 month also, trust weight, to completely hydrate proteins. It's not a easy thing to understand. So the solubility varies because of all these properties. I'll come back on the drying thing in the next slide also. Now I'll come back to the maximum solubility. Okay, it's a real solubility according to me. What do you mean by maximum solubility? Is nothing but how much protein can really dissolve in a given solution. Okay, not under a specific condition. Okay, it's not under a specific condition. How much protein in a given volume of water or any other solvent, how much it can dissolve. That's called maximum solubility. And this is a very tedious experiment to do, almost impossible in more cases, right? Why? Because you do it in this way. You take protein powder and put it into water containing glass or beaker or whatever, falcon tube here. Then you need to stir it forever. Because the protein solubility is a very slow process. Okay, every half an hour, let's say 0.0001% protein is solubilizing. Okay, imagine that's the property of your protein, because protein has to hydrate. That means the water molecule should go and hydrate every individual moiety so to come into solution, and that takes a lot of time, right? And that can take even up to 2 months sometimes. I was reading an article, if you really want to determine the maximum solubility, you need to stir continuously for 2 months. Of course, I don't have 2 months for my PhD, right? So we don't do it in food science often because that information is not necessarily needed in some cases. So just to tell you that if you really want to find out the real solubility, you need to give a good conditions to and find out the actual solubility. You slowly add more and more and more and more and more, stir, and measure every time. Okay, when do I see no concentration difference? And that will be the maximum solubility. And we don't do it often. Have you done it in your PhD? No. Make sense? So this is the curve. Basically, you have protein concentration. There is no protein, no solubility. Increasing the protein concentration in this direction, solubility increases. Now the blue is pure protein. Imagine you have an ultra pure one protein, individual protein. Okay? And the green one is isolate. Isolate is, let's say, mixture. It's always mixture of 10 different or 100 different proteins. Okay? Mixture. If you have an individual proteins, let's say ultra pure only one type of protein, then solubility increases continuously. At a particular point, it will stop solubilizing because you're completely saturated. No more solute molecule is interacting with the solvent molecule. Then you see the no solubility change. But in case of mixture, you never get this sharp thing. You'll get this bent thing. Why? Because you have numerous proteins playing. I want to solubilize, I don't want to solubilize. I want to solubilize, I don't want to solubilize. So in that cases, you don't get a sharp change in the solubility. Just to show you don't get really like this beautiful curve. It's an illustration. Just to let you know that the mixture, you have a different solubility property compared to individual proteins. Okay. One of the disadvantages, it takes for a long time. And then coming back to the predictive solubility, you have been asking this question that how do we know which one we're solubilizing more and which we don't solubilize more? Easiest thing is to do trial and error method. Take all the proteins, do solubility test. But nowadays we have something called AI, artificial intelligence and machine learning. Now, not for all the plant proteins, at least some of the plant protein sequences are available. You go to PDB and you find the protein structure, your complete amino acid sequences of some of the plant protein, not all. not all, some of the plant proteins. Milk you have, almost every individual milk proteins have been crystallized. You have absolutely beautiful structure of milk proteins. Plants we don't have, but still we have some. And if you know the amino acid sequence, if it is in the database, they can create the three-dimensional structure nicely. And they know which amino acid is on the surface, they know which amino acid is buried. If there is a more and more polar amino acids on the surface, what it will happen? It will solubilize more, it likes water more, right? If there is more and more non-polar amino acids on the surface, it will not solubilize more. You can determine these properties in the computer directly using machine learning, okay? And you can also determine the theoretical PI of the protein. What is PI? Isoelectric point, the lowest solubility. You can also find out the theoretical isoelectric point if you know the individual amino acid composition. You can calculate it theoretically. And when you know the surface properties, when you know the folding behavior, when you know the theoretical PI, you can predict the protein solubility. But it's not very easy in the plant-based world. Why? Because of the complex proteins, one of the reasons. The second reason is it's not an individual one protein. You have 10 to 20 to 30, 40 different varieties in one protein isolate, and this computer also goes crazy, right? Because they're talking about individual proteins, but we don't have individual proteins there. We have a mixture of proteins. So the property what you're measuring is a mixture of everything. So to predict that is also very difficult. Am I clear? So the easiest thing probably at the moment may be the trial and error, but if you develop this AI modeling, it's an important field nowadays. This is also something career you can take in the future, AI in food science, that can revolutionize things. Then people don't have to do a lot of laboratory work. There's apparently a lot of models for that. I have no idea about what these models are. I just mentioning it here. If you're interested, go and Google about this, okay? These are the models to predict the solubility. One of the disadvantages, as I mentioned, it's very complex system, then you cannot measure. Now we will look a little bit about the different factors affecting the solubility. Now we'll be discussing about the solubility, and I'll talk a little bit about different factors affecting the solubility. The first one is temperature. Now, I have a beaker containing water, and now my protein is inside, completely soluble, imagine, or partially soluble, right? Now I'm slowly heating this beaker now, okay? What are the effects you will see? Don't read all these things written on the slide, just think about it. I have a beaker containing proteins, I'm slowly heating it now. What are the effects you will see?
Protein denatures.
The first thing she was thinking that the protein might denature because proteins are folded, right? And this folding is because of which bonds?
Peptide bonds.
Hydrogen bond. Peptide bond is also true, but hydrogen bonding. Peptide bonds you can't break by just heating, right? You need a strong acid. So hydrogen bond can be easily broken, not very easily, depending on how many hydrogen bonds you have, can be easily broken, and proteins can denature, right? Every protein has its own denaturation temperature. Have you heard about it? Right? Some protein will completely denature at 80 degrees, some will be 50 degrees, some will be 90 degrees, some will be 100 degrees Celsius. For example, rapeseed protein has two proteins called napin and cruciferin. Napin denatures around 100 and 110 degrees Celsius. Cruciferin denatures around 80 degrees Celsius because they have a different temperature when they denature. So one of the things you can observe, the protein can denature. Anything you observe when you're heating?
When the protein unfolds, there will be a change in the bonding.
Yeah.
Like when it unfolds, the hydrophobic may come outside, or hydrophilic, whichever is buried, may come outside.
Yeah.
And it interacts more with the water, and so the solubility will increase.
I think I have a point here. Can you read this one? It's a very good suggestion. But I'm writing that thermal denaturation decreases the protein solubility. What could be the reason? You're right. I'm not telling you wrong. But sometimes the solubility is also decreased.
Yes, because of aggregation, it may decrease.
Exactly. Now this is a mixed behavior effects. Can you see what she is telling? When you're heating, this was originally folded proteins, so now it's denatured, right? And she's telling the water molecule can interact nicely and protein will solubilize. She's also telling this is not the case. When you heat it, it denatures and then it interacts with other proteins. It becomes a bigger particle and precipitates. Am I clear? So it's very difficult to say what exactly is happening depending on the protein and the temperature you are applying and the heat you are applying. It makes sense? Heat load. So when you denature, protein can get more water molecules into excess. It might solubilize, but in many cases it's not solubilizes. Why? Because interaction will be with water molecules may be less governed compared to protein-protein interaction, because you will expose hydrophobic regions quickly. Okay, you will expose the thiol groups, right? The protein will have so-called thiol groups like this. Okay, and another protein will have a disulfide bonds like this one, and then you will favor the thiol disulfide bond linkages, and you will get a protein with linked by disulfide bond, and that will give you the protein aggregation, and solubility can be compromised. It's a very difficult and important phenomenon to understand. That means you can't say the solubility is increasing. If you see increased, you are happy. If you see decreased, then you know the reason. Make sense? All right, now let's move on to some examples here. So in solubility of Mung protein isolate, you can clearly see that at lower temperature also they have the decreasing solubility and no effect in the solubility. That's what the mixed effect. So it depends upon the type of protein, the solubility varies with respect to temperature. Now, in this case, they are actually doing this experiment where they actually took this Mung protein isolate and they did the ultrasound treatment along with heating. Then they saw kind of increased solubility. What could be the reason? Reduction in the particle size. So ultrasound, remember ultrasound I taught you last time? You put this beaker containing protein and you put ultrasonic probe, use it for the extraction, but ultrasound is not only doing the extraction, it will also reduce the particle size. When you reduce the particle size, surface area increases, interaction with water molecule increases, solubility increases. But people also say that it will also improve the hydration of the molecule, ultrasound, because of the cavitation phenomenon. I'm not very sure it's true or wrong, not. But they also say that it improves the hydration of water molecule by entrapping the water molecule on the surface. There are a lot of theories, but there is no proof for that one. But they can improve the solubility. Okay. pH. Can anyone explain? I'm a little bit tired now. Can anyone explain how pH would affect solubility? Take a mic, just talk for 2 minutes. You're welcome to do that. How pH would affect solubility?
So this again we can go back to the isoelectric point of the pH.
Exactly. So we go back to our previous lecture. So we have pH, we have solubility. Can you explain me how would the curve look like?
The curve would look like this.
The reverse bell shape, right? So it can have a high solubility and solubility decreases, no solubility, and then increases. This is what you see often, solubility. Now, could you please explain me why you see the highest solubility here? At lowest pH, you have the higher solubility. What could be the reason?
At lower pH, protein will have more sites for bonding.
Yeah, more sites for bonding. What exactly that site?
The OH negative. And
OH negative.
they will interact with the water H positive.
So he's talking something about the charge, right? Now, can you tell me, I have a protein, okay? This is my protein. The pH of the solution is 2.0. What will be the charge of the protein? Likely they will be positively charged. Do you agree? Why? Because the amino groups on the protein from lysine will be protonated. Arginines will be protonated. So protein will get net positive charge. Do you agree? Positive charge is ionic. Water likes ionic compounds. So protein solubilizes here. In this region, proteins will be positively charged. The positive charge decreases when you increase the pH. So the solubility decreases. Here, you will find higher solubility. What could be the reason? More negative charge, because you will have more deprotonation. The carboxylic acid will become CO minus. So the protein will have more negative charge. Negative charge is ionic. Water likes ionic. So solubility increases. What exactly happening here? No net charge, because there is a 50% positive, 50% negative. So the protein have plus minus, and so on, minus plus minus, so on. Equal charges attract each other, they precipitate off. Clear? Please don't forget this curve. Okay, it's an important curve, you have to keep it in mind. It's very useful to do the alkali extraction of your protein, right? This is exactly what we do. We extract the proteins here, we precipitate the extracted protein here, right? We extract the proteins here, we precipitate the extracted proteins here, exactly based on this phenomenon. Am I clear? But I will explain a little bit beyond these things now. Just think carefully. Usually, alkali condition also denatures proteins. Okay, why? Because when the protein is here, this three-dimensionally folded, you have a disulfide bonds, right? It is known that because of alkali condition, because of this OH, strong OH minus ion, this disulfide bond can be broken. There's a lot of theories about that one. I have already told about, and I'll come back to that later. Just for now, you just remember that this disulfide bond can be broken because of beta elimination reaction, because of OH, this one. Now the protein becomes open like this. Can you see? You get an SH group or something like that. Now the protein denatures, what happens? I was telling, when the protein denatures, aggregation happens, right? Because you will allow more and more protein aggregation. But if you have more and more protein aggregation, protein has to precipitate. But the protein don't precipitate here. Can you tell me why? Now two phenomena are happening simultaneously. One, proteins are getting negative charge. Meantime, proteins are also denaturing. But still we see highest solubility. What could be the reason? I mentioned in this region, the protein will be having negative charge. Okay? And the negative charge will help protein to solubilize. But in the same region, the protein can also denature. When the protein denatures, they tend to aggregate. That's what I told you in my previous slide. So I also expect the protein to aggregate and precipitate, but we don't see any precipitation often here. What could be the reason? Because the charge is more than the aggregation. Why? Why there is no aggregation?
The alkali condition that we give
Yeah.
is more and more when compared to the aggregation.
So she is telling that the effect of getting negative charge is overshadowing the
Yes.
effect of denaturation.
Yes.
That's what your explanation. Okay, I fully agree with you. But actually, that's true. What exactly happens in this particular region? The protein gets negative charge. Other proteins, everything gets negative charge. To aggregate, two proteins would come together. Do you agree? When they aggregate, they come together, then they aggregate. Now the electrostatic repulsion. Now everything is having negative charge. They want to come together because they want to aggregate, but you have a negative charge on the surface. Ionic bonding is very, very strong. The repulsion is so strong, it pulls away, so they don't aggregate and precipitate. Does that make sense? So I'm talking about two different theories here, and which one is more governing than the other one. Another important observation we can make in this particular figure. Can you carefully look into this figure? I'll give you 30 seconds. Look into this figure and give me an observation.
Sunflower globulin and pea globulin are not same.
She's telling that the globulins are not same. I agree. Any other thing?
Depending on the protein fraction, the solubility changes.
Depending on the protein fraction, solubility changes. I agree. But what exactly you're observing in terms of solubility? I'll give you one hint. Can you compare globulins and albumins here?
So globulins have a very predictive solubility, the trend which we expect.
Yeah.
But albumins have a very unpredictable
Can
behavior.
you see that one? The globulins have a beautiful curve, what I've just mentioned, like this one, right? In both the cases. Albumins, look at the solubility percentage. Can you see here? Who is soluble, more soluble? Who is soluble? Albumins. Can you see? Albumins are more soluble. That's one particular observation. Second observation, as he says, globulins have a very predictive solubility depending on the pH. Albumins are crazy. And not only that, you don't have a very clear PI pattern. Can you see here? This is the PI we call most often in food science, but you don't see a very clear PI here. And even at a different pH, we're talking about 1 to 11 here, is soluble. How much? 80%. So this phenomenon, what I just explained over here, not applicable to every proteins. Okay. Please note that albumins having a greater solubility, even though they have a particular PI, they might have high solubility in their PI. Make sense? Albumins do have a PI, but don't believe a fact that every protein will have the lowest solubility at their pH. That is not true. Albumins can be soluble to a greater extent at their pI. Is that okay? Does that make sense to you? Because they don't have this clear predictive solubility curves. Am I clear? For example, nipin is a rapeseed protein. I think it has pI around 10 or something like that, if I'm not wrong. And it's completely soluble in a very long pH range, albumin. Okay? And it's an important thing you have to keep it in mind when you do protein extraction. When you do protein extraction, you extract it alkali condition. Do you agree? You extract it pH 11, for example. Then you do isoelectric precipitation. You often use one pH. What is that? 4 or 5. Do you agree? You use 4 or 5 as an isoelectric pH. And then you precipitate the protein and you freeze dry it and you say, oh, I got a lot of field. But actually, you're only extracting globulins. Can you see? Albumins are still in the supernatant. Why? Because albumins are still soluble at that particular pH. Does that make sense? So when you do extraction study, be careful that don't believe you're precipitating everything. No, you're only precipitating the small portion. Often you lose a lot of albumins in isoelectric point precipitation if you work with the plant proteins. Supernatant still has proteins. That's our albumin. It's very important to mention why, because it's a good thing in the plant-based world because most of the storage proteins are globulin, fortunately. We get a lot of proteins. We're very happy about it, but you still lose a lot of albumins. But albumins have a different functional property than globulin. So if you really need albumins, you need to refractionate the supernatant. Make sense? And you can see I got this very nice figure from this very nice research review article. They have tried to combine the PIs of show the solubility profile of different well-known plant proteins. One trend you can see. What is the trend here? Most of them globulins, and they can also see this nice curve. Can you see? And the PIs or the least solubility is always in this range. Can you see? 4 to 6. So most of the plant-based protein isolates apparently shows PI 4 to 6, maybe because of globulins, which is also good because you can use this isoelectric precipitation around 4 to 5, 4.5 or something to get the most of the protein during the extraction. Am I clear? Okay, now we go for the ionic strength. I have told you in my very plus class, albumins are water soluble, globulins are salt soluble, prolamines are alcohol solubles. Okay, so remember this figure, salting in and salting out. I don't teach it again today, right? You remember the salt extraction? I told you protein solubility is highest at the low some concentration of salt, and then it decreases, right? And this region you will have more when you have protein. When you have another protein, the protein will have some charges here, right? When you have a salt, it shields the charges, avoids protein-protein interaction, and increases protein-water interaction, and the protein solubilizes. When you have very high salt, all the water molecule will be taken by the salt to make a hydration. Then the protein-protein interaction happens and protein precipitates. I have taught you already. I don't explain you this one again. So you can use this phenomenon for the salt-based extraction. Am I clear? So here you can see that how different salt concentration affecting the solubility of bran protein concentrate. You can see that when you have solubility with water is this much. When you have a small amount of sodium chloride, solubility increases. When you have a very high amount of sodium chloride, solubility decreases. And this is because salting in, and this is because salting out phenomenon. I had explained that one already in my previous class. Okay. And the solvents also affect the solubility. If you add alcohol, protein precipitates, right? But prolamines will solubilize in alcohol, especially 80 or 70% ethanol you can use to extract proteins. Alcohol precipitates protein, you know, right? Usually for protein precipitation in our laboratory, especially biochemistry people, molecular biology people, they add alcohol because alcohol denatures the protein. Alcohol remove the accessibility of protein to water molecule, and protein precipitates because of protein-protein interaction. So don't add alcohol if you want to increase the protein solubility, right? It will denature the protein. But if you want to extract prolamines, you need to use around 70% ethanol. And coming back to your question, drying and freezing, and it has a huge impact on protein solubility, freezing and drying. Because when you freeze dry for a long period, you remove the hydrated water molecules. It's very difficult to remove hydrated molecule, but they still say that water molecules which on the surface of the protein will be removed, and then the protein is kind of a dry, naked position now. And now that dry protein, that you have protein powder, and then you did freeze drying or lyophilization, and then you get a very dry protein. And the dry protein basically having a structure that is so dry, it does not want water molecule now, right? There is a good intermolecular interaction now. It takes several hours to stir at room temperature or in the fridge to rehydrate the protein. So if you freeze dry your plant-based proteins, don't directly put into water and then just do vertex and then don't use it. It's a bad idea to do the research like that. Okay. If you at all you freeze or spray dried the protein, it's very important to rehydrate your protein minimum 2 hours, maximum several days. You need to do that experiment to see how much protein I can dissolve. 2 hours is usually minimum. I don't say it's universal fact, but I generally do minimum 2 hours stirring. But overnight stirring is recommended to improve the solubility. Then the protein will be hydrated and dissolve. Protein has a good solubility, but it does not like water any longer. If you stir it for a long period, it starts liking it and then it dissolves. Is it okay? Same thing is true with freezing. It's not recommended to freeze thaw proteins, because when you do the freeze thaw, small protein crystals will be formed inside the protein cavity between the particles, and that will denature the protein, ice crystals, micro ice crystals. It's okay to freeze your protein. You do lot of laboratory experiment. You can't finish experiment in the same day, right? You can't do extraction and functionality analysis the same day. So you need to freeze the samples. It's very normal. However, always I recommend that don't freeze it in a bulk big box. Freeze it in several tubes, right? You take the 1 tube per day that for that particular analysis, right? Don't refreeze it again. Take the other tube for the next day, next experiment. Does that make sense? You freeze dry a big batch, and then you divide it into, or you freeze the big batch, but you divide it into multiple tubes, and don't try to do freeze thaw. Freezing and thawing, temperature fluctuation will create ice crystals, and that can denature your protein, that can affect the solubility, that can also affect the functional property. But it's only to a minor level for most of the plant proteins, but it might happen. Okay. And the solubility is also depending on the other component present in the food. There's something called phytic acid. Have you heard? I'll talk a lot about that later in the other classes. It's an anti-nutrient. It contains inositol moiety with a lot of phosphate groups, right? And this phytic acid interacts with proteins and decreases the protein solubility. So one of the important point I want to tell you, almost most of the legumes or the seed proteins basically contains phytic acid. It is an anti-nutrient. It binds to metal ions. Phytic acid can also bind to protein, and they can affect the protein solubility. Okay, keep that in mind. It's often ignored point actually. We don't worry about phytic acid and solubility, but actually it can severely compromise protein solubility. So you need to remove phytic acid. How do we remove phytic acid? You can add phytase enzyme. Okay, so this is one of the experiments you can do in your also work. To improve the solubility, you can remove the phytic acid. All right, we will take a break after 5 minutes after this one. Then protein modification can also affect the protein solubility. As I said, proteins containing amino acids, and if I modify this amino acid with other things, the surface properties of the protein will be changed and the solubility will be changed. For example, if I modify the protein with the sugar contains OH group, maybe solubility will be increased. If you modify it with the, let's say, polyphenols, solubility can be increased. or sometimes solubility can also be decreased depending on what exactly happens to the protein. A lot of enzymes we do, for example, we can convert protein glutamic acid, glutamine into, we can convert into glutamic acid, and the glutamic acid gives the negative charge on the protein, and that can improve the solubility. So we can try to change the, I'll talk about this thing also in another exclusive lecture, okay? And the other thing is that if you have a protein, it's insoluble now. If you do a partial hydrolysis, it can become more and more soluble. You can use enzymes to do the partial hydrolysis. You can do fermentation to do the partial hydrolysis. You can add mild acid to do the partial hydrolysis. When you change the structure of the protein, the solubility can be changed. But you can also compromise the functional oil property if you do the hydrolysis, just to let you know. Okay? We still have to talk a little bit about water holding capacity, emulsification, and foaming. But since I have given a very good background to you about solubility, the rest of the things will become much easier for you. I really wanted to spend more time on solubility because the other things are also a little bit related to solubility and the protein structure and so on. Okay, let's start with water holding capacity. And if you look into any alternative based proteins paper, they do solubility analysis, then immediately they start doing water holding capacity. It's the common analytical methods we follow to characterize the functional properties of known or unknown proteins. So, what do you mean by water holding capacity? There are a lot of definitions, but there is nothing about clear definition in food science. The water holding capacity is nothing but it's the ability of the protein to retain the water molecule which is bound on its surface, right? The ability of protein to hold water, that's water holding capacity, right? Ability of protein to hold water. And there is something like that, you have to keep it in mind that it's not simple holding. If you apply some pressure, if you apply some centrifugation forces, if you do some stretching and bending, still that water should be on the surface. And that is the determination of water holding capacity. Does that make sense? I have some nominal common definitions here. When you're free, just read through them. But in general, it's nothing but the capacity of proteins to hold the adsorbed hot water on its surface or the hydrated water on its surface. People call it as it's something the water that cannot be freezed at minus 40 degrees Celsius. Okay. Now, if you remember about solubility, right? We had a beaker containing water, and protein is added, right? Now, it's very simple to solubility also, okay? It's not nothing different than that one. So, when you have a protein here, and if you have water molecule have a fantastic structure. They have O and H, right? Remember that they have a delta negative and delta positive here, right? Protein is also a very complex molecule, and it has lot of structure, like you have a carbonyl group sometime. Oh, sorry, it's a bad carbonyl group to write. English, it's on the peptide bond, but I'll just show it in this way. We have a carbonyl group from the peptide bond. We have amino group. Okay, we have carboxylic group. We have sulfahydryl group. So many different groups we have. Some are charged, some are uncharged, and some we also have something containing ring, for example, phenylalanine, right? And they have some properties to love or hate water molecule. Do you agree? For example, we all know that the ionic compounds like water because of the ionic interaction, because they have a delta positive and delta negative, right? We also know that if you have a carbonyl groups, they are having the property to create hydrogen bonding, right? Oxygen is electronegative, and then it can make a hydrogen bonding with water molecule. So, water tries to interact with proteins in different ways. Sometimes you have some ring structure, they don't like water molecules. They try to pull the water away. So, it's basically hydration of water. How does exactly it happens? Is that you have a protein molecule, the water tries to adsorb on the surface as a layer. It adsorbs on the layer by layer. You have a first layer which is strongly adsorbed, and then you have a second layer, and you have a third layer, and so on. Finally, you have a very loose layer. It depends upon the pulling capacity of the protein molecule. Protein is a chain, imagine, and your water molecule is attached on the surface. It's basically the water holding. Can you see here? Please note that this water molecule, what I'm pointing here, is different than the water present outside. this is the adsorbed water, the hydrated shell, and you have also water molecule here, and that is called bulk water. Is it clear? Two different types of water molecule I'm talking about. Water that's adsorbed on the surface of the protein and water that is moving around the protein. They are different. The water it's adsorbed on surface of the protein basically have a restricted mobility. It cannot move because it is attached to the protein now. But water is present around the protein inside the solution that can move. So that is the difference between hydrated water and bulk water. Does that make sense? Usually the water holding capacity is determined by these particular types of water that's somehow attached on the surface of proteins. Am I clear? So that is the water holding behavior. Why it is very important? Because we need meat which is juicy, right? And the juiciness of the meat is simply because of the water holding capacity of the protein in the meat. For example, in the true meat, we have myofibrillar proteins and so many other proteins, and that proteins have a high water holding capacity, so that makes the meat juicy. Now, if you want to create plant-based meat analog, that has to be juicy. In order to make them juicy, you need to add the proteins or create the proteins that is having a little bit higher water holding capacity. Because when you put them into the mouth that is released, you get that juiciness, right? And this should not be a bulk water, because the bulk water, what happens is that when you remove the protein, the water molecule falls down. That water we don't want. We want the water, it's attached on the surface of the protein, and that is the water holding capacity. That's a hydrated water, and that gives you the nice texture, the juiciness to the food products you're going to create. Does that make sense? Clear. So now I will show you a little bit about how the interaction happens. As I said, I have already explained this one. Imagine this is my protein, the orange ones, right? The water molecules can be adsorbed on the surface like this one, and the bulk water molecules can be here. But we are more concerned about the water molecule attached on the surface, okay? As I said, they can form layer by layer. That keep it in mind. It depends upon how many layers that can make. It depends upon the capacity of the protein to pull that water molecule, because the interaction could be because of hydrogen bonding, because of the ionic bonding, and so many bonding. So ionic bondings are really strong. For example, if you have a protein with a lot of NH3 plus, right, then you get a more hydration shells like this one. Then if you have a protein with like you have let's say a peptide with the carbonyl group, basically they tend to make a one hydrogen bonding with one water molecule, something like this one. Sorry, it should be this way. So the layer density can vary depending on the protein you have. That's the reason why the amino acid composition, the primary structure of the protein, is very important. If you have more and more ionic amino acids, probably you will have a better water holding capacity, right? It also depends upon the folding of the protein, because if you have a more hydrophobic structure on the surface, it might have a less water holding capacity, it might have a more oil holding capacity, right? Because the hydrophobic amino acids, they don't like water molecule, they just want to push. So the folding is also important, but usually hydrophilics are surface exposed and hydrophobic are buried, so they show you to a certain degree of water holding capacity. Does that make sense? Again, the water holding capacity is also dependent on too many parameters. For example, protein concentration, pH, ionic strength, temperature, presence of other components, on all these things. But these things I have already explained you in the solubility parameters. Exactly the same thing applies here. Solubility is nothing but the first step of water holding capacity. First water start interacting with this one, and then it solubilizes. So whatever the parameter that's applicable to solubility, usually the same parameters are also applicable to water holding capacity. So I don't have to explain that in detail. Is it okay with you? So for example, just to give an illustration, just to refresh your memory, how pH affects, you remember the curve In the isoelectric point, there is a more protein-protein interaction. There may be different water holding capacity compared to non-isoelectric point conditions, right? Ionic strength, you remember the salting in and salting out effect, right? If you have some ions, they can shield the charge and they can change the water holding capacity, right? If you have high temperature, that can denature the proteins, that will expose more hydrophobic residues, and then maybe water holding capacity can be reduced. Why? Because water does not like hydrophobic regions, it likes hydrophilic regions. Then the storage condition, it's basically during storage, what happens is that protein can be denatured slowly, then you can change the water holding capacity. Then also important thing is that what is the other component attached to the protein, because they also determine the hydrogen bonding. For example, if you have a polyphenol attached on the protein, and this OH group can also create a hydrogen bonding with water molecule, right? You can have a hydrogen bonding like this one, and that can again change the water holding capacity. So, and that's the reason why in every single alternative protein research article, they will measure water holding capacity, because they are very sure that depending on the processing, depending on the extraction condition, depending on the treatment they are doing, there will definitely some change in the water holding capacity, because the protein structure changes, water binding capacity changes, and the value, what we call water holding capacity, gram per gram, that will also change. Make sense? So, how are we measuring water holding capacity? How many of you measured water holding capacity? Perhaps you have done it. I don't know. How did you do, if you can recall?
I have taken 5 gram of protein.
Yeah.
I have added water to it.
Yeah.
Then I have centrifuged.
Yeah.
I have taken the initial weight, that
Yeah.
5 gram.
Yeah.
After that, after centrifugation, I have decanted the water.
Yeah.
And again, I have taken the weight of the sample with water.
Yes, she took 5 grams of protein and she added how much amount of water?
5 ml.
So she added 5 ml of protein, 1:1 volume here, and then she centrifuged, or sorry, shook, vortexed or something did you do? So she vortexed. Did you wait for some time?
Yeah.
Yeah,
I
she
don't
must have
remember
waited some
exactly.
X minute. It's okay. And then you basically get a suspension here, right? You get a suspension, and then you centrifuge that suspension, and you get a pellet and the supernatant. And you carefully discarded the supernatant, and then what you get the pellet. Okay, I think you have weighed this one. Did you say that one? Yeah, so you took the weight of this one before adding the water, right? You took the weight of this one before adding the water, and you took the weight of this one after removing the water, and the difference divided by the original weight will give you the water holding capacity in percentage or gram per gram. Does that make sense? This is the most common method that we use today. I also copy pasted this method from one of the research articles to show you can use this method without any problem. The idea is simple. You have a protein, you add an X amount of water, right? Then the water will go and bind to the surface of protein, as I mentioned previously, in a different layer, right? And then you centrifuge. When you centrifuge, what happens? The hydrated water, the bind water, the adsorbed water will not be removed. Am I clear? Because they're tightly bound on the protein surface. But those free water, the mobile water, will go away because of the centrifugal force. When the protein precipitates, it will bring protein along with the hydrated water, but it will release the non-bound or free water. Now, if you take the difference in the weight, that will give you the water holding capacity. Make sense? It's a very simple experiment to do, in my opinion. Often people define in recent literature, water holding capacity is nothing but amount of water bound to per gram of protein. It's a normal definition in the recent article. How much amount of water in gram can be bound or adsorbed or hydrated on per gram of protein is called water holding capacity. And that is a table you will see in every research article. I can show you one example here. just to compare, just ignore this one for now. Just to compare different, this also you ignore. I'll come back to later. Soy protein isolate, pea protein isolate, fava protein isolate. I think it's lupin or no, lentin protein isolate. So you can see the difference in the water holding capacity. I have been keep praising soy protein, right? Soy is extensively investigated simply because soy has every single functional properties in a very good level compared to any other plant proteins. You can also see that it really has a very good water holding capacity, and that is the reason why most of the products sold in the US market at the moment containing soy, especially the plant-based analogs, meat analog, chicken analog, beef analog, egg analogs, everything contains soy. It's simply because that gives you this juiciness, because it contains, it has a really good water holding capacity, equivalent to the common meat-based proteins actually. So that's really cool. The factors affecting the oil holding capacity, you need to be while measuring this oil holding capacity, you need to keep in mind of these things that often people ignore. The first one is protein concentration, because if you change the protein concentration, oil holding capacity, water holding capacity will change, right? And centrifugation time and the G value also important, and hydration before measurement is also important, because she mentioned that she vortexed and she kept it for some time. If you kept it for a longer time, you will give more time for hydration, and then the water holding capacity will also change. So there is again, I've been reading some article, is there any uniform method people are following? Am I correct? No methods. Everybody follows their own protocols depending on the type of centrifuge they have in their laboratory, to the best of my knowledge. If their centrifuge cannot run for a faster speed, they can't do that one. So that's a problem. So there's no uniform method here. Again, we need to have a standardized method to measure water holding capacity, and that's the reason why I really enjoyed reading this particular paper. I think this is from Julian McClements from University of California, Davis. It's from Davis. I think it's from Davis. He made a really nice comparison, comparing 4 different commonly used proteins and how they show different functionalities using the common analytical method. It's very difficult to compare between paper to paper. We can compare the data within the paper. So they compared it and they can very clearly show that soy protein isolate has a really good water holding capacity. All right, now we'll little bit move on to the next important topic, oil binding capacity or oil binding properties, which is exactly similar to water binding properties, but an opposite one. Do you agree? Oil and water. Oil has a hydrophobic carbon side chain, triglycerides, right? They're opposite because oil is non-polar. Do you agree? Water is polar. So in case of protein, what happens if you have a polar residues, let's say amino group, it likes water molecule, right? Because polar interaction or ionic interaction. But if you have a non-polar residues, let's say leucine or let's say benzene rings and so on, they don't like water, they like oil. So basically, instead of getting the water layer, you will start getting the oil layer on the surface, and the capacity of the protein to hold oil is the oil holding capacity, just opposite to the water holding capacity. Is it clear? So the protein can have both oil holding capacity and water holding capacity, because proteins are kind of amphoteric. That means it has both not amphoteric is a bad word to use, sorry. It has both polar region and it also has non-polar region. It has hydrophobic region, it has also have hydrophilic region, and that's the reason why the protein is an excellent oil binder and also water binder, right? It has a dual properties. It varies depending on the composition of the amino acid plus folding. Usually denatured proteins can have a better oil holding capacity. Why? Because you expose the hydrophobic region and the oil can bind nicely and you get a higher oil binding capacity. I really want to tell you one thing is that the processing impact the oil and water holding capacity. That's the reason, because you denature or renature the protein depending on the processing, heat treatment, and the purity also matters. If you have an impure proteins, it may have a different oil binding capacity compared to pure proteins. Why? Because the other components present in the proteins can also interact with oil, okay, or water. So the oil binding capacity can change. So be careful about that when you measure the protein purity, and the condition and the concentration, pH, and everything matters while determining the oil holding or water holding capacity. How do we determine oil holding capacity? Same as previous experiment. Instead of adding water, add oil. What type of oil do you use here? Do you remember any type of oil? Which one did you use? Organic sunflower oil. That's nice to use. Okay. In fact, I have seen papers showing different oils. Some people use rapeseed oil, some people use organic sunflower oil, some people use sunflower oil, some people use soy oil. Different oils have been used to measure oil holding capacity, and there is no universal common oil to be used. It depends upon which oil you want to finally you want to interact it. So you're welcome to use the oil you want, but if you want to compare it with different papers, try to use the same method and same oil. Then you can make a comparison data. Make sense? So again, there is a lot of factors affect the oil holding capacity. In it, similar to the water holding capacity, I don't explain that in again. But one of the things you have to think about while measuring the oil holding capacity, what you do is that you take a beaker, you weigh the protein 5 grams, what she meant, and she added organic sunflower oil. Okay. And she measured then the oil holding capacity. It's very important to know that, especially if you use proteins coming from the seeds, leguminous seeds, they already contain some oil. Keep that in mind, because depending on the extraction, whether they have used air classification or whether they have used hexane extraction, depending on that, there is always a trace amount of oil already present in the protein, and that might actually affect the oil holding capacity. So the true oil holding capacity can be compromised if it's already having other oil. Make sense? So it's very important to keep that in mind when you measure oil holding capacity. But it's very difficult to remove that oil present. That's a big challenge, because to remove that oil you need to do hexane extraction. If you do hexane extraction, you will denature protein. If you denature protein, oil holding capacity will change. We are in a problem now. Now I'll show you a little bit about curves, which I wanted to mention how different factors affecting the oil holding capacity. I found this from this book, and they show clearly that increasing the protein content, oil holding capacity increases, but the temperature has no effect. Okay, especially for oh my god, I forgot to mention which oil it is, which protein it is. I think it was from pea or sunflower. I think it is from sunflower protein isolate, but we can check it in this paper. In case of wheat germ flour, again, they see that increasing protein concentration increase the oil holding capacity, but the temperature has very minimum effect. But it's not always the case. For example, in this case of corn germ oil, increasing protein concentration increase the oil holding capacity, and at a particular temperature they found highest oil holding capacity. So temperature does matter, and that varies depending on the type of the protein. Okay, but in general, if you increase the protein concentration, you will definitely get more oil holding capacity. Okay. Now this is a figure that is showing how different processing affect oil holding capacity. You can see that this is sonicated samples. This is non-sonicated sample. Sonication is ultrasound treatment. You can see that when you do ultrasound treatment, oil holding capacity increased. Can you see? When you do the ultrasound treatment, oil holding capacity got increased. It's simply because probably ultrasound denatured the protein, probably exposed to hydrophobic moieties. Maybe oil is more interacting with the protein surface, so increase the oil holding capacity. What I want to tell you here is that the processing matters. Depending on the type of processing you're doing, the oil holding capacity and water holding capacity can change. Here is another example of how different proteins and their oil holding capacity from the same paper. You can see that soy has the highest water holding capacity, but it also had a very good oil binding capacity. That's the beauty of soy. It's an all-in-one protein in plant-based world. It can do many things together, many jobs simultaneously. But in this case, if you ignore the standard deviation here, no, there's a statistically insignificant. You can see that everything. So they are all having the similar oil holding capacity. Make sense? Now we will move on to the emulsifying properties of proteins. Oil and water never mix in normal temperature and pressure condition. They never mix. But you take oil and water and you shake vigorously, right? For a couple of seconds at least, you see they're kind of mixed, not really mixed. They're kind of mixed. Do you agree? You start creating kind of an emulsion because of this vigorous shaking. What exactly is happening here? Oil droplets can be broken down into small pieces, become a micro droplet because of this vigorous shaking, and it will try to disperse within the water phase. Do you agree? Because in this case, at least, if you imagine you have a higher volume of water and lower volume of, let's say, oil, and when you shake it like this, you get a small oil droplets within the water phase, and it creates kind of an emulsion. In this case, if you have more oil and less water, basically within the oil phase, you'll get a small droplets of water. So water in oil emulsion. So by shaking, you can start creating the emulsions. Am I clear? In real life. Now, by definition, emulsion is nothing but dispersion of two or more immiscible liquid. That's very important. Two or more immiscible liquid, one of which is dispersed in the other as a small droplets. Okay, it's basically you have two immiscible liquids. So this is liquid number 1, L1, and the L2 is a small droplets. This is L2. Okay, and that is called emulsion. Am I clear? Both are immiscible, but the other one is dispersed in the another one. Basically, dispersion of one in another as a small droplet, and that is called emulsion. It's a nice example I got. These two things are not emulsified, but this one is really emulsified. Can you see? And when you add an emulsifying agent, you will create a nice emulsion. It's a stable one. It is where emulsification is extremely important. Why? Because we would like to use this plant-based protein for insect proteins in solution in many cases. We want to create sports drink. We want to create liquid infant formula. We want to create yogurt. We want to create milk. And after creating them, we would like to put it in the supermarket shelf. If you have a phase separation, people won't buy that one, right? They really want something in a single phase. If you have a mayonnaise, for example, mayonnaise bottle you buy from the supermarket, if you have an oil phase and if you have a water phase on a mayonnaise, do you buy it? You think it's something is wrong with this and I don't want to buy. It has to be really a good single phase, a good emulsion. And that's the reason why emulsion and emulsifiers are very important. Emulsion is important to get a structure, a good taste, good texture, sorry. And emulsifier is important to stabilize the emulsion. Am I clear? Now I'll talk about two different types of emulsions: oil in water emulsion and water in oil emulsion. It's very simple. As the word says, in case of oil in water, this is oil in water. Water is the bulk one, oil is the droplet. Am I clear? In water in oil, water is the droplet, oil is the bulk one. Oil in water emulsion and water in oil emulsion. There's a lot of examples. For example, milk and mayonnaise are all oil in water emulsion. Margarine and butter. Butter has a lot of fat, so it's basically water in oil emulsion. These are the normal examples. Any doubt about these two things? Okay, we can have two types of emulsions, oil in water and water in oil. In case of oil in water, the droplets are, the micro droplets are oil, and water is the immiscible liquid here. Now, how do we create emulsions? As I said, the easiest way is to take two immiscible liquid and shake it, you get the emulsion, but they are not stable. Within a minute, within a half a second, they get a phase separation, all right? To avoid this one, we do homogenization, because the homogenization will help us to create micro bubbles or micro droplets, and it will create the homogeneous micro droplets in the bulk of oil or water. So homogenization is one of the common technique used to create emulsion. Do you remember ultra 2x in the laboratory? You can also use ultrasound, but ultrasound is one of the efficient way to create emulsion. I mean, as I said, you can take a spoon and do it like this one, but the problem is it's not efficient. We need to put a very high shear rate to the emulsifying liquid here to create these micro droplets. And to get that one, we use an equipment called ultra 2x. Okay, and that can create these micro droplets like this one within the within water or within oil, depending on oil in water or water in oil. Okay. We also use one of the equipment called high pressure homogenizer. Have you used it? It's also one of the most efficient instrument to create emulsions. Okay. High pressure, this is the one equipment, we also have it in our own lab. What we do here is that we take these two immiscible liquid and we put it into this particular chamber here. And inside this one, they actually pass through a very narrow space at a very high pressure. We're talking about pressure, if I'm not wrong, maybe more than 200 or around 2000 bars. It's super high pressure. And because of that high pressure and homogenization, a micro bubbles are formed. Just to show one example here, we put the product in here, right? And they're mixed here under a very high pressure, and they're passing through the very narrow chamber, right? This is illustrated in more here. You have oil droplet, for example. Now it's a bigger in size. Can you see? Right? And they are passed through the narrow chamber, and then they have a Y splitting. They split it into two different tubings here, and they come back in this region in a very narrow space, and they collide each other. When they collide each other, they create a very shear stress here, right? A very shear stress. Because of the collision of the droplets, you get a micro droplets, right? Now the bigger droplet becomes smaller droplets, then you get a very fine emulsion. And this is one of the most commonly used method to create a very stable or homogeneous emulsions. Okay? We use high pressure homogenization, HPH. Now, we talk a little bit about the emulsifiers now. Now, if I talk about emulsion, let's say oil in water emulsion, this is oil droplets, and this is water, and this is oil. Okay. Now, we need a stable emulsion. Do you agree? The emulsion should be stable. That means if you put it in the supermarket shelf, if you put it in your kitchen, we don't want to have a phase separation. We want them it homogeneous as much as possible. But it's very difficult to have a homogeneous emulsion in reality. We need to stabilize this emulsion because the droplets, they have a crazy behavior. When they have a small droplets, initially because of the homogenization, you create a small droplets, but these droplets can interact with each other because they are so close to each other. They interact with each other and they can create another new phase now. We don't want to have the surface interaction between the droplets to avoid that one. So to avoid this all interactions, to create this very stable emulsion, we add an emulsifier. Okay, emulsifier is nothing but that is a reagent, it's a chemical that stabilizes the emulsion. It will also help to create smaller droplets. I'll show you how. Emulsifier has two properties. It has both hydrophilic and hydrophobic tail. It is amphoteric in nature. It has both hydrophilic moiety and hydrophobic moiety. Okay. In case of, let's say, oil in water emulsion, you have an oil droplet, right? Oil is non-polar in nature, right? and this emulsifier will place in such a way that its hydrophobic end will attach to the oil and hydrophilic will go to the water phase, right? Hydrophobic attached to the oil and hydrophilic go to the water phase. So it nicely surrounds the water oil droplets nicely. Now, since it surrounds the oil droplet, if I have a new oil droplet, now imagine here, it's a new oil droplet, but the surface of this oil droplet is hydrophobic. Do you agree? It's hydrophobic. Now, the surface here is hydrophilic. Can you see? And they don't interact each other. While you're creating this, when you're doing homogenization, if you add an emulsifier, so when you're doing homogenization, when you add emulsifier, basically when the new droplets are forming, it will avoid the interaction between the droplets because it will create a barrier. Can you see? Right? Not only that, it covers the surface of the droplet, it will stabilize the droplet so the droplets won't interact with other droplets, because now this is hydrophobic and this is hydrophilic and this is hydrophobic. There is no interaction. Am I clear? And that's how it will start helping you to create very small droplets in the homogenizer. The opposite is true in case of oil and water emulsion, where the water molecules are hydrophilic, so the hydrophilic region of the emulsifier interacts with the water droplet and the hydrophobic region interacts with the oil. And that is how the emulsifier will stabilize the emulsion. Emulsifier is a reagent. It will help us to stabilize the emulsion. It will also help us to create small micro droplets. Now I'll tell you how protein acts as an emulsifier. Okay, how protein has an emulsification behavior. Let's explain how protein acts as an emulsifier. Now let's take it in water in oil emulsion. There's an example here. Now we have a bulk of oil and we have a bulk of water, and this is oil droplet. Okay. Now I'll add a small amount of protein, plant protein for example. Now I added a small amount of protein. Protein is three-dimensionally folded. Okay. Protein also has a behavior like a true emulsifier. It has a hydrophilic. It also has hydrophobic region, hydrophilic region, right? Because protein is made up of amino acids. Some are hydrophobic and some are hydrophilic, right? Some contains OH group, for example, and that gives the protein also dual properties, hydrophilic and hydrophobic. Now you add that protein to water containing oil droplets, right? Now what this protein will do, if it has a very good emulsification properties, it will slowly migrate towards oil. The first step, okay? It will migrate towards the oil, and then it will start orienting in a way that the hydrophobic region of protein will interact with the oil and the hydrophilic region of the protein will interact with the water. That's the second step. First step, diffusion, migration. Second step is orientation, where it will orient in a way that hydrophilic region of the protein will interact with water, hydrophobic region of protein will interact with the oil. Okay, then it will slowly denature. Okay, it will denature, then it will orient nicely. And the last step, it will cover the oil droplets nicely. Okay, it will cover the oil droplet nicely, three-dimensional, exactly in this way. Okay, and that's how it will stabilize the proteins. Is it clear how protein acts as an emulsifier? Okay, in oil and water emulsifier, protein will go slowly. It will attach on the surface of the oil droplet. It will denature it and it will orient properly in a way that hydrophilic region go to water side, hydrophobic region go to oil side, and that will create a stable emulsion because now protein will surround the oil droplets as a thin film, and that will help in emulsification. Now, factor affecting the emulsification properties. So we have a pH that has an effect and protein concentration has an effect. Exactly the same thing what I've explained in previous slides. In isoelectric point, they have a more aggregation. And if you have an ionic, if you have positively charged proteins in a different pH, they migrate in a different way. If you have a negatively charged protein, they migrate in a different way. They orient in a different way. They create a hydrogen bonding in a different way. So pH affects the emulsification properties. It's often people measure that when how pH shows the emulsification index. Same thing is true with ionic strength, which I have already explained the solubility. Now I have one example here, the emulsification capacity of whey protein, which is a milk protein. So you can see that depending on the protein concentration, it increased and then it decreased, right? You need to find out the right protein concentration to create the emulsion. Otherwise, it will destabilize the emulsion. Please note that when you talk about the emulsification, we need to add a small amount of protein. If you overload the protein, what happens is that it creates a new phase. It's no longer an emulsion. You start precipitating the protein, so you destabilize the emulsion. So the critical emulsification protein concentration has to be determined. Okay. And please note that when you want to use protein as an emulsifier agent, it's not for the nutritional purpose. It's just for the emulsion purpose. It's not about adding more and more proteins. It's adding the right amount of protein get the emulsification properties, not to get the nutritional benefit. Okay. And here is the emulsification properties of different soy types. They have a soy flour, soy isolate, and soy concentrate. And this is the isolate, this is the flour, this is the concentrate. What did these guys found was that temperature had a minimum role on this one. And also the very interesting point that they say that even though they have a different purity degree, they did not see a much difference in the emulsification property, but you can always compare the y-axis here. Flour had a little bit higher than the concentrate, and the isolate also had a very high emulsification property. So depending on the degree of purity, you get a different emulsification properties. Okay. But I don't want to cover these 2 points, but you have read it in a research paper. They talk about emulsifying activity, emulsifying capacity, emulsifying stability. Emulsifying stability is nothing but how stable is emulsion during storage or different treatment. Okay. Now, how do we measure the emulsification properties? There is a lot of techniques to measure emulsification properties, but we often use in alternative world droplet measurement, right? Finding out the droplet size, because whenever we say emulsification, it's basically formation of droplets, right? The droplets can be of different size. The number of droplets and the distribution of the size of the droplet talks about the emulsification capacity or efficiency here. Okay, total number of droplets plus the size distribution of these droplets within the emulsion talks about the emulsifying properties, and the size distribution of the droplets can be measured using what we call master sizer. Basically is it measures the particle size based on the light, because the light will be, I don't know if it's a refraction or diffraction phenomenon, I forgot completely now. The light will be, the property of the light will be changed based on the, is refraction? Diffraction? Diffraction. So the property of the light will be changed based on the size of the particle. It diffract in a different ways, and you get a different particle size distribution, and that can be used to measure the emulsification properties. Okay. Here is one nice example I found. They show that how different protein concentration affects the particle size distribution. You can see that increasing the protein concentration decrease the particle size, right? Increasing the protein concentration decrease the particle size, so the droplet size. And they're also trying to compare different protein isolates and their droplet size. You can clearly see that which one had the highest one. In general, the gray one showed the highest, biggest particle size. It's fava, right? You can see that the soy, which is the light gray, this one, it gives the small particle size. And the beauty is that when they use the lentil protein isolate, so that's over here, that gives you the lowest particle size. That's really good. We can say that the lentil protein isolates can be used to get lowest particle size. But please note that it's very important to know the protein concentration as well. We don't want to add a lot of protein into to get the emulsification property. No, that's not the idea. We need to use a small amount of protein because then it's sustainable. I'm telling you again, we are not adding protein to get a nutritional benefit. No, we're adding the protein to get the functional property here. So it's better to add a small amount. Then you save money, right? In that sense, I think this paper shows that the lentil is the best protein to use. If you really want to study emulsification properties, you can go for reading this particular paper. They have a lot of information about the emulsification property. So now I'll only take 15 minutes for foaming. Foaming is important. You know chai? We just had chai, right? And when you look into these YouTube reels, the chai walas, they make like this. Have you seen? Right? Why do they do that one? They get the foam, right? The foaming is an important functional property. If it's an aesthetic property, we want to see that foam. And Horlicks advertisement, have you seen? You drink and they get something on this here, right? The foam, right? If you come to Europe and America, cappuccino is one of the most sold beverages, and that has a foam. They bubble hot air, I don't know, this like hot milk to coffee, and then you get this foam. So the foaming is very important. Ice cream also has some kind of foam, right? It's an important functional property. I don't know how, for me it's not important, to be frank. I don't care whether chai has a foam or not. I just need chai. But for some people, foaming is very important. It is an important functional properties. What do you mean by foam? Basically, foam is nothing but it has air bubbles. In emulsion, we have oil bubble or water bubble, right? So here we have an air bubble, right? And they're not a bubble in that, it's a droplet. Here it's actually we have an air bubble, and that air bubble is actually covered by a thin layer of liquid. It could be water in this case, right? And that is foam, right? Foaming capacity is something very important because once you make this chai like this, right? And he get it in the glass and he'll bring and give it to you, right? You should have that foam at least until you start drinking, right? If the foam disappears immediately, then there is no use of foam, right? That's what we call foaming stability. Two things are important: foaming capacity and foaming stability. Foaming capacity is how much foam can be formed, right? We should not have too much foaming also, because then basically you take Coca-Cola, for example, right? You go to McD or you try to take a Coca-Cola. If you pour it so fast, you'll only get a little bit Coke and too much foam. We don't want that also, right? And we need to find a fine balance between foaming and the stability is important, means it should be stable for some period so that the consumer can consume it. If it disappears immediately, there is no use of foaming. That's the reason why capacity and the stability of foam is important. We're going to talk a little bit about foaming, how exactly foaming forms. It's very similar principle as I just explained in the emulsification. What exactly happens here is that when you take, let's say, water and about small amount of protein, let's say in this case 10%. So you have water, this is water, and these are the proteins, right? And then you do whipping. Whipping is like shaking or doing like this one or bubbling air, whatever it is, right? When you supply high flush of air, whipping, then basically there is a formation of air bubbles. Can you see here? Right? Now we have three things here. One, we have water, we have protein, and we have air bubbles, right? Now, protein has again these properties. It has hydrophilic region and hydrophobic region, right? Hydrophilic region likes water. Hydrophobic region likes, in this case, non-polar, I think it's air, right? It slowly diffuses toward the air bubbles and it will orient in a way that the hydrophobic region will go towards air interface and hydrophilic region will go towards the water interface. It will slowly cover the air bubble. All right, and thus it will stabilize the foam by stabilizing the air bubble. But does that make sense? It creates the thin layer around the air bubble upon denaturation of the protein. Very similar to the mechanism I explained to the emulsification. In the emulsification, the surrounding of the protein happens on the bubbles, the droplets, right? In this case, it surrounds the air bubble. That's the only difference, okay? How do we measure foaming properties? There are different methods, but at least in a food science, we use this common approach. We take the measuring cylinder and we add water and we add our protein, and we can supply air if you want, or you can shake what you want, but usually we supply air, right? We supply nitrogen or carbon dioxide, and then the foaming occurs. Then because of the foaming, the volume of the foam increases in the measuring cylinder. Because it foams, then the foam increases like this one, right? Then if you have a time versus length here, or percentage of or volume, okay, initially you get a high volume of foam until here, right? Maybe 80 ml, let's say. Over the time, slowly the bubble collapses, right? Then the foaming decreases like this one. After half an hour, after 10 hour, after 30 hour, after 3 months, I have no idea. Depending on the stability of the foam, this curve goes down. Am I clear? If we have a very stable foam, this curve, the time will take forever. Okay? If you have an unstable foam, it will drop quickly. Does that make sense? That is the foaming capacity. This is foaming capacity. This is foaming stability. How long it can go, though in terms of volume, is foaming capacity. How stable it is in terms of time is foaming stability. And that can be measured easily with this flask experiment. Again, it depends upon the air bubble the air you supply, the length of the breadth of the measuring cylinder, a lot of parameters, and I did not find any research article they follow the same methods. Everybody have their own methods here also, but you're also welcome to follow your own method, but report carefully what exactly you have done. So I have some examples about foaming stability and how that is varying with respect to pH. You can clearly see that they have high foaming stability at pH 6 compared to 7 compared to 8. I would like to mention that pH matters here also in the foaming, simply because pH changes the three-dimensional structure of the protein. When protein denatures or renatures, its surface properties changes. How it covers around the air bubble also changes. Depending on that, you get a different foaming capacity and foaming stability. Okay. And here is a nice example of different plant proteins and their foaming capacities. Let's look into the y-axis here. You can see that the cowpea can go up to 90-ish, and peanut can also go up to 90-ish. Soy can also go up to 90, 95-ish. So all the plant proteins, or most of the plant proteins, really have a good foaming capacity. It's more about foaming stability, how fast they drop. And that varies depending on type of processing, right? For example, if you have pure proteins, they might have a different foaming capacity. If you have a partially hydrolyzed proteins, they might have a different foaming capacity and different foaming stability. We often do proteins and we hydrolyze into small fractions, and they might have a different foaming capacity. So basically, depending on the processing condition, you can change the stability as well as the capacity. And there is nothing called that you need to have the best foaming stability. Best foaming stability is also sometimes problematic. We need to have a balanced foaming stability to get the desired foaming properties for the given food prop, right? All right, and that's it.